few weeks I will get time to realize it's right before my eyes and I can take it if it's...
Hello and welcome to the concepts video on logarithmic functions. So I'm going to start the discussion on logarithmic functions by talking about exponential functions first. Just a quick review, don't worry, this isn't going to be a whole nother video on exponential functions. But what we had before were that exponential functions such as the form 2 to the x, e to the x, 4 to the negative x, and so on and so forth. We had exponential functions of this form, right? Some kind of a times b to the x. But now we're going to see that their inverse functions, so the ones that kind of undo the effect or reverse the effect of these, are called logarithmic functions or log functions. Logarithmic functions, okay? So what do I mean by this? So let's say we have some f of x is equal to b to the x, right? This is an exponential, okay? So this is our exponential function, okay? And b is called our base, alrighty? That's just the terminology it's given because this is a base and raised to a certain exponent or raised to a certain power, okay? And now our inverse of that, the inverse function, is going to be log, which stands for logarithmic, so log base b of x, okay? So this is the inverse function of that, alrighty? So it follows that b to the a is equal to c. So if you have some base raised to a power equaling a certain number, then this is the same as saying that our log base b of c is equal to a. I know it looks a little bit weird, but this is just how the inverse relationship works, is that when you write your log, we write our base on the bottom, okay? Our exponent kind of goes on the right side, on the other side of the equation, and our result comes right here, right after the log part, okay? So let's do some examples, because it's a little bit tricky, but once you get used to it, you'll be fine and good to go. So let's say we have 2 to the third is equal to 8, okay? So that's true, 2 cubed is 8, okay? Nothing big there. But we can write this as a log as well. So we could say log base, we write our base here, and our base is 2. We write our exponent on the other side of the equal sign, and then we write our result right here. Okay, we kind of just squish it in there. Alrighty, let's do one more example of these. So 3 to the negative 2 is equal to 9, 1 over 9 that is. Okay, and we would have log base 3, and then we could also write 1 over 9 here, that's our result, and then is equal to negative 2. Okay, so it's just a matter of like switching things around, okay? Something like that. So since we have, since exponential and log functions are inverses, we have the following relation. We know that f of f inverse of x should output an x, as should f inverse of f of x. So basically when you compose functions which are inverses, then you just get back out whatever you put in originally, okay? So this means that in this case, we could have b raised to some power. So what we're working with is b to the x and log base b of x, okay? So if we compose one in the other, that would basically mean we're taking an entire function and sticking it in the x spot of the other function. Okay, so this would mean b and then raised to the log base b of x. Okay, this is just going to output an x because they're inverses, they have to output an x like this when they're composed. Okay, we can also compose them the other way. And what do I mean by that? So if we have these two functions here, let's say, we can take one function and stick it inside the x value or the input value of the other. So then this one would look like log base b of b to the x. This also has to equal x because our exponential and log functions are inverses, so they must output, when they're composed with each other, they have to output the same input. Okay? So these are really important relations here, and they'll become super useful when you go to solve some problems and you really want to just cancel things out. Okay? So here's an example. We have rewrite this expression here, this logarithmic expression or equation, as an exponential equation and then solve. Okay, so we have a base of 4, so that means our base is going to have to be 4. Our exponent is found on the other side, so we're going to raise that to the third power, and our result is in this spot, so that's just going to be x. So x is ultimately just equal to 4 to the third, which is equal to 4 times 16, so we're just going to get x is equal to 64, and we're done. Okay, so here's another example we could do. If we're going to solve this equation for x, well, what should we do first? So we have 2 to the x is equal to 10. Okay, so what we really need to do is make use of the fact that exponential and log functions are inverses, right? So what we're going to do is actually take log base 2 of each side, okay? And the reasoning why I'm going to do this is because these cancel out on the left. You see how we have the same base for these? So those are 2 is like b, okay? So that means that when we have a log with the same base right next to the exponential form, then we can cancel those out, and we just get the x back, okay? So x is equal to log base 2 of 10, okay? And that's pretty much it. That's as far as we can go without a calculator, okay? And so this is our answer. So the important thing to note is that we're going to kind of think of log. So just a tip here is think of log base b of x and our b to the x, so our log and exponential, kind of as, well, they are inverses. We're going to think of them like opposites, okay? Kind of, sort of. Kind of like addition and subtraction, like opposites in the sense that their net or overall effect is 0 when they're used together, okay? Or when used right next to each other. When used together, okay? Alrighty, so now here's some more, here are some important definitions that we're going to run into. So the first is called the common log, okay? So what does that mean? Well, we're not talking about trees here, but the common log is basically of this form, log base 10 of x, okay? So the common log just means that we have a base of 10, because 10 is such a versatile number, and we can use it to take powers of things, right? So since it is so common, sometimes we just write this as log of x. So whenever your base is invisible, that usually means it's a 10, okay? That's usually meaning it's referring to a 10. Okay, the other definition, or the other term that I want to introduce is what's called a natural log. Okay, and this has to do with the natural number, and the natural number is e. So this is going to be log base e of something, okay? And usually we write this, like most commonly basically, we write this as ln of something. And I think that stands for like log natural something or other. But anyways, maybe in a different language or something. But we just write ln. This is the most commonly used and seen form of our natural log. Okay? So let's do a quick example using the natural log. Let's say we want to do, so let me write an example here, ln of square root of e. Okay? So you could think of this as something like, usually we don't write it, but in the beginning you can. So log base e, that's like our natural log, and then e to the 1/2. And we see that we can actually cancel these out because they have the same base, right? And we just get out a 1/2, and we're good to go. So now let's go over some properties of logs, okay? Properties of logs, and logs refers to logarithms, okay? So what we have first is called the exponent property. Exponent property. Okay, so what does this mean? This is, let me just write the rule and then I'll explain what's going on. So we have log base b of a to the r is equal to r times log base b of a. So basically what that means is that when you have, when you're taking the log of something and you have that something happens to have an exponent, we're always welcome to move that exponent right out in front and make it the coefficient. Okay? So, for example, let's say we had log base 3 of 25 or something like that. This is equal to log base 3, and we can just break up the 25 into like 5 squared, let's say. So according to our exponent property or exponent rule here, we can move that 2 all the way out in front. So we get that this is equal to 2 times the log base 3 of 5. And that's how you would simplify it. Okay. Another property that it has, that logs have, are change of base. Change of base, it's called, okay? And this one is the following. If we were to have like log base b of a, we could always rewrite this as log base c, and c can be anything you want it to be. A over log base c of b, okay? So the important thing here is that we're kind of just splitting it up, and I always remember which one goes on top and which one goes on bottom by it's kind of like the placement of things, right? So the A would go on top because it looks like it's above the B anyways, and the B goes on the bottom, and then you can use whichever base you'd like, okay? And oftentimes we use the ln, or the natural log, so C is equal to E kind of thing. So usually we say something like this: log base B of A is equal to the same thing as ln of A over ln of B, okay? And that's just commonly used, not always. Okay, so let's finish off this concepts video with an example. We have a population grows from 100 to 130 in 2 weeks. Find the continuous growth rate. Okay, so let's say we measure t in weeks, okay? And let's say when t equals 0, okay, when we first started measuring, then our population was equal to 100, okay? And when t equals 2, so like after 2 weeks, now our population is at 130. Okay, so basically what these are telling us is if we were to say P represents the model or the function that models population, we could say P of 0 is equal to 100 and P of 2 is equal to 130. Okay, and we know because we've learned before the formula for continuous compounding or continuous like interest kind of thing, right, or rate of change, then we have the formula A times E to the RT, or to the Rx, or whatever you want to say. Okay, so this one here is equal to A times E to the R, whatever R is, we're looking for that, and then the T is just a 0, okay? So this tells us this whole thing is a 1, so that's going to be A. So A, which is like our principal, our initial amount, is going to be 100, okay? So now we know A is equal to 100, which helps us for this second equation, and it allows us to set up 100 times e to the RT, and t is 2, right? And I'm just taking from this information here, t is equal to 2, okay? So now we have this 100e to the 2r, okay? So now we have the equation to solve, which is given by 130 is equal to 100e to the 2r, okay? So now our aim is just to solve for r. Alrighty, so let's just move on to the next slide to finally solve this equation here. So we have 130 is equal to 100 times e to the 2r. Let's divide the 100 over. Okay, so we divide by 100 on both sides, and we get e to the 2r is equal to 1.3. Okay, and now to get this exponent down, we have to get past this e here, this exponent. So what we're going to do is do the opposite of exponential, and we're going to take a log. And in particular, we're going to take the natural log because we're dealing with e, right? Our base is e, so we're going to take natural log on both sides. So we're going to ln both sides, right? And these cancel out on the right side, so we just get 2r is equal to ln of 1.3. Okay? So finally, r, when we divide by 2, r is simply going to be equal to, well, not simply, but ln of 1.3, and then divided by 2. And when you plug this into your calculator, we get something around 0.1312, which tells us that the rate, this is it represented as a decimal, so the rate is going to be 13.12% per week as for the population growth. Population growth rate. Okay? And that is it. Alrighty, so that wraps up our concepts video on logarithmic functions. That's kind of a tough word to say. I hope that helped, and I'll talk to you in the practice problems video if you want.